Hello, Chem 1B. This is chapter 19, lecture video 5, and we're going to do a cell EMF problem here. And so we read the problem. We have a cobalt 2 plus cobalt solid half cell and an AgCl or Ag plus Ag solid half cell, and we've connected them. And we want to know if the reaction is spontaneous, what is the cell potential, and what reaction occurs at the anode. So you got to understand here what's going on, right, to really get this problem. So if we think of like a beaker, right, and let's do it different. And we have a liquid in there, right? We got liquid, and we have our, anode, and we have our salt bridge into a different beaker. Right, and we have our other anode, or our electrode, and these electrodes are connected by a wire. What we're being asked is, okay, we have in this one CO2 plus aqueous, and this electrode is cobalt solid, and in this one we have like Ag solid, and this liquid is Ag plus aqueous. We want to know which one of these cells is going to be the anode and the cathode. And in order to do this, we need to know a couple pieces of information, right? We want the reaction to be spontaneous, and so based on that statement, which one's the anode or the cathode, and what's our cell potential. So we know if the reaction is spontaneous, then E naught cell must be greater than 0, right? So let's look up our reduction potentials for both of our two half reactions, the cobalt 2 plus going to cobalt solid and the Ag plus going to Ag solid, and we get these values. So at this point we can just kind of take a whack. Maybe this is the anode and this is the cathode. Actually, I'm going to take a guess on the other way. Let's say this is our cathode and this is our anode. Well, I know E naught cell is equal to my cathode's reduction potential, so negative 0.277 minus my anode, 0.222. And if I do this out, I get negative 0.499 volts. So this can't be the right answer. So I know that then this must have been the anode, and this must have been the cathode. So, meaning that I flip those in the equation, right? So cathode minus anode, so now it's 0.222 volts minus negative 0.277 volts, giving me positive 0.499 volts. And that's my answer to the cell potential. Now we need to know, okay, what's the reaction occurring at the anode? Well, we know anode is oxidation, right? So these two things, the cobalt 2 plus and cobalt solid, must be an oxidation half reaction. So I know that the cobalt solid must be turning into cobalt 2 plus because that's the oxidation version, and plus 2 electrons. You could be asked. We can calculate E naught cell for the following cell and then say, hey, is this reaction spontaneous? So there's a couple things that we can tell just right off the bat from this multiple choice question. So we got a bunch of reduction potentials given here, and we know our equation E naught cell is equal to the reduction potential of the cathode minus the reduction potential of the anode. Now, that's great. We have all these values, we can calculate them, but I always like to go over some ways to eliminate some answers from our multiple choice questions. For instance, I know E naught cell has to be positive for a reaction to be spontaneous. And for instance, I can see, hey, this is negative. and it's saying the reaction is spontaneous, so that's not possible. So that answer is wrong. And so I can eliminate at least one answer now, and this increases my chances of guessing if I were to guess. But nonetheless, we have this cell notation, so I know my anode is Fe, solid, going to Fe2+, plus 2 electrons. Now this is an oxidation, so I'm looking for the opposite of that. In other words, this is my anode. At the same time, I know I have gold 3+ going to gold solid as my cathode. So I have gold 3+ plus 3 electrons goes to gold solid, which means this is my cathode. It's an ugly color. Cathode. Now we can do our calculation, right? So I can go, okay, well then E naught cell is equal to 1.50, my cathode, minus my anode, a negative 0.45. Or in other words, 1.95 volts. And this is going to be my answer because this is a positive value, which means it is a spontaneous reaction, and here's the value that we calculated. So that's a pretty simple multiple choice question that you could be asked to do. All right. So to continue talking about this, the more positive our reduction potential, the stronger the oxidizing agent is. This is bringing back a vocab word from Chem 1A. And the more negative a reduction potential is, the stronger the reducing agent. In other words, as our reduction potentials become more positive, it is more likely that substance is going to be reduced rather than oxidized. Hence, oxidizing agent. Oxidizing agents are the thing that oxidizes something else. In other words, they are being reduced themselves. The more negative our reduction potential, the stronger the reducing agent, meaning the more likely this guy is going to be oxidized. Does that make sense? So, a species with a really large positive reduction potential will usually spontaneously oxidize something that has a very small or negative reduction potential. We can kind of think of that in terms of E naught cell calculation. In other words, if we look at this reduction potential table, it's in order of decreasing as we go down that way, or increasing as we go up this way. And since as we go up this table, the values become more positive, we have the values becoming stronger oxidizing agents as we go up. And since as we go down the table, the values become more negative as we go down, like you can see here, we have stronger reducing agents. In other words, sodium plus down here is a really strong reducing agent because of its really negative reduction potential. Whereas chlorine gas is a really strong oxidizing agent. If I put these two together, spontaneously what will happen is the chlorine, this guy, will be reduced by the sodium, which will in turn be oxidized. That'll happen spontaneously. If we can force a reaction that's non-spontaneous to occur, go the other way, but it takes energy. Anyways, rank the following species from strongest to weakest reducing agents, right? So we got I-, we got Fe solid, and we have Al solid as well. And we want to know which one of these is going to be the strongest, which one is going to be the weakest reducing agent. Now, how do we do this? Well, we got to look up some values. So we look up the reduction potentials of each one of these guys, and those are them. And at this point, just using that relationship we just learned, we can determine which one is the strongest or weakest reducing agent. We know reducing agents are stronger when they become more negative because a reducing agent is something that's going to be oxidized. So I can see that this value here, use a different color, this value here is the most negative, and this one is the most positive, which tells me that as we go, this way, we have strongest to weakest reducing agent. So our strongest reducing agent is the aluminum, then we have the iron, then we have the I-, the iodide. Again, remember, the more negative your reduction potential, the stronger reducing agent, the more positive, the stronger the oxidizing agent. So one more problem. List the following metals in order of increasing oxidizing agent strength. This means E not red, more positive, is what we're looking for here. So the one with the largest positive reduction potential is going to be the strongest oxidizing agent, whereas the one with the most negative reduction potential is going to be the strongest reducing agent, or the weakest oxidizing agent. I can see very clearly that this guy is my most negative value, which means it's going to be my weakest oxidizing agent. And since we're going in order of increasing, we want it first. So that tells me right then and there that it's either one of these two answers, because those are the ones that have Fe2+ as the starting point. After that, I need to go in order of increasing positive. More positive, the reduction potential, that's what I'm going in order of. So if we look at this guy here, this is just slightly more positive than this guy, so we're going to do Fe3+ next. Hey, that's this. E has to be my answer, but we can keep going. This one's more positive than that, so gold 3+ would be next, and then cobalt has the largest positive, so it would be last. So E has to be my answer, as you can see. All right, so this is a very, I don't want to say it's a simple question, but it's the simplest question we see in chapter 18, and we can continue on. So there is a definite relationship between E naught cell, delta G naught, and the equilibrium constant. We know the relationship between these two already. That's delta G naught of reaction is equal to negative RT ln of KEQ. We learned this equation in chapter 17. But there's actually a relationship between these two as well, which means if there's a relationship between these two and there's a relationship between these two, there's also a relationship between those two. So let's look at that. We know how to predict spontaneity 4 different ways, right? Delta S universe has to be positive, delta G has to be negative, the equilibrium constant has to be greater than 1, and now in this chapter, E naught cell has to be positive. Now for us, we're going to focus on these 3 values: positive E naught cell, negative delta G, and larger than 1 KEQ. What we also know is that the maximum work a system can do is defined as negative delta G. We learned that in chapter 17 as well. Now, that's just any old work. Electrical work, however, is defined as charge times potential. Potential being E naught cell. So charge, this Q here is our charge variable. And we know that this is equal to negative delta G naught. Now, this is Q charge. This Q is in coulombs per single electron. Now, generally in a voltaic cell, we have a lot of electrons moving through our system. So doing it per electron is a little funky. This is more of a physics calculation. They usually use per electron. We're going to be using per mole of electron, which means we're going to use what's known as Faraday's constant, F. And I will give you this on the test. You don't have to memorize it. And Faraday's constant is 96,485 coulombs per mole, or joules per volt per mole. This is the unit we like better. It's one we use more often, but both are totally equivalent. You could use either one. Now, this changes this equation a little bit up here to something new. For a reaction where we have n number of electrons transferred, and this is really like n moles of electrons transferred, we have delta G is equal to n, negative n, F, E naught cell. Now, F in this case is Faraday's constant, 96,485 joules over volts times moles. And like I said, this is moles of electrons transferred in the reaction, and this is, E naught cell. Using this equation, we can kind of go back and forth between these two variables. I will provide this equation on a test, so you don't need to memorize it. Okay, so let's say we have this reaction here, and we want to determine delta G naught using E naught cell. All right, so we're going to use E naught cell. Now that means I need to calculate E naught cell, which means I need reduction potential. So first thing I'm going to do is I'm going to split this up into the half reactions. Oh God, this is out of order. Oh, sorry. No, it's not. I just need to write it in. Ni2 plus is going to Ni solid here. And CrOH3 is going to, this is a solid, is going to CrO4 2 minus. Now, this guy's oxidation number is 3 plus. This one's 6 plus, so I know chromium's being oxidized. This is 2 plus. This is 0, so this one's being reduced. And these are the reduction potentials I can look up from a table, or you'd be given them a lot of times. In other words, I know this guy's being reduced and this guy's being oxidized, which means E naught cell is cathode minus anode. Cathode is the reduction, anode is the being oxidized. So in other words, E naught cell then for this problem has to be equal to negative 0.28 volts minus a negative 0.13 volts. And I can get E naught cell here for this. It should be negative 0.15 volts. And this is my answer for E naught cell, as you can see. Now, I know this is a non-spontaneous process, according to this equation, which means I should expect a delta G, once I eventually calculate it, of positive, because delta G is negative when it's spontaneous. When it's non-spontaneous, it's positive. So we should be expecting a positive delta G once we eventually calculate it. All right, so let's move on to the next step. We need to figure out how many electrons were actually transferred. Now, in order to do that, we need to multiply these so that the electrons are going to cancel. These are the balanced half reactions, just like when we're balancing a redox reaction. Now, this tells me 3 times 2 or 2 times 3. I have 6 total electrons being transferred. All right, and this is really 6 moles of electrons being transferred, technically. We do not add the 2. No adding. The electrons that are being used here were the ones that are formed here, right? So you can't just go, oh, well, it's 12 total. No, it's these same 6 are then being used here to reduce the nickel. So just be careful about that. So I know that N is 6. Now I have my equation, right? Delta G naught of my reaction is equal to negative NF E naught cell. Now we calculate E naught cell on the last slide. Faraday's constant is a constant. N is 6. We can solve. All right. Now you got to be careful here. Generally, delta G is given in kilojoules, so that's what this part here is. I'm just converting to kilojoules. but I have 6 moles of electrons times Faraday's constant. I rounded a little bit, times our E naught cell. And we get positive 87 kilojoules per mole as our answer here. And this is how we can go between the two. Now, to see how the equilibrium constant and E naught cell are related, we have to take those two equations, right? We know delta G naught is equal to negative NF E naught cell, and we know delta G naught is equal to negative RT ln of KQ. So we can combine these two equations. This guy is equal to that. Or in other words, rearrange. Sorry, hold on. Out of order. Rearrange, and we get this equation. I'll give you this equation on the test. Don't worry about it. The book uses another equation, and I don't, for the life of me, know why. This one works technically at any temperature. This one only works down here. This guy only works at 25 degrees Celsius. And basically what they did was they plugged in RT for you and put that there. And I don't know why they did this because it's just one button click different in your calculator. They changed to log. I hate this equation, to be honest with you. This is the one I'm going to be providing. Use that one. It works at any temperature, in any condition, as long as we're understanding conditions still, because this is an E naught value. If you use the first one, you'll always get the answer no matter what temperature we're at. This one only works at 25. Use whatever one you want. I mean, you can use this one by all means, but I'm not going to give it on the test. And I don't like it because it tends to lead to simple mistakes. So, all right, so that's the end of Chapter 18, Video Lecture 4. If you have any questions, please email me.